All right, let's get right into it. If you've been following the Non-Holomorphic Bird Map series, you know that papers 19 through 24 were this massive, deep hunt along the real axis. Well, today, we're cracking open the case file for paper 25. And this is, well, it's the off-axis sequel. Think of it less like another paper and more like a detective story that takes the whole investigation into a brand new dimension, the complex Borel-Plane.
So, here is the central mystery we're up against. We already know the non-holomorphic perturbation, G of mz, it completely wiped the Feigenbaum Singularity off the real axis. But what did it actually do to it? Was the singularity just pushed sideways, hiding somewhere in the complex plane? That's what the paper calls outcome A, displacement. Or was it completely annihilated, outcome B, destruction? That is the one question paper 25 is designed to answer.
Now, to really get what's happening here, we have to look back at the cold case files. All the previous work built this enormous 6-ladder, 2-family atlas searching for this singularity, strictly on the positive real Borel axis. It was an incredibly meticulous search that ultimately came up empty. And the result from that was totally unambiguous. Every single probe we had, from the gamma family to the conformal family, found nothing in the Feigenbaum window. So, the case on the real axis? Officially closed. But it left this huge question just hanging there. What if we were just looking in the wrong place the whole time?
So let's meet our lead detective for this complex plane investigation. It's the battle-tested Gamma Family Pade-Borel engine. We know this tool well. It's been calibrated with just extreme precision, right? Using parameters that map our search target right to S equals 1.0 in the Borel plane. This is the exact tool that built that whole real axis atlas, and now it's getting repurposed for an off-axis search.
And this is the crucial leap in paper 25. You see, the Pade denominator, Q of S, it was always a polynomial in a complex variable. Its roots, just by definition, live in the complex plane. The previous papers were only checking for sign changes on the real axis. It's like a detective searching just one single street in a whole city. Paper 25 finally unleashes the engine's full power, using numpy.roots to find every single complex root. The search grid just exploded from a line into a plane. Of course, before you send a probe into totally uncharted territory, you have to be absolutely sure it works. You can't go looking for an unknown target with an untested tool, right? So the very first step was this rigorous G-force synthetic calibration to certify the engine for complex searches.
So the calibration had two really critical tests. First, a sort of backward compatibility check. Could it still find what it was supposed to find before? We planted a known pole right on the real axis at S0 equals 0.19013. Then came the big one, the new test. We planted a genuinely complex pole off the axis at 0.19013 plus 0.1i. The question was simple. Can this engine actually find a target that's not on the real line?
And the result? Just perfection. In both of those tests, the engine recovered the exact location of the planted pole with machine precision. We're talking an error on the order of 10 to the minus 17. The probe was certified. Our detective was now confirmed to be stable, accurate, and totally ready for the real investigation in the complex plane.
Okay, so with the engine calibrated and certified, it was time. Time to deploy it on the real data. And this wasn't just some spot check, this was a comprehensive sweep across all 6 of those established data ladders from the previous atlas.
And this is the full search grid. Both the Aether limit and the Class C regimes were examined, and we're covering all 3 key observables, the orbit multiplier, the WBA, and the alien strength. This wasn't a random sample. No, this was a systematic sweep of every single key observable. If that Feigenbaum singularity was hiding anywhere in the complex neighborhood of these series, this search was designed to find it. Now, in any good investigation, you need clear rules of evidence to avoid false positives. The first one is complex G1, or Pade stability. For a potential pole to even be taken seriously, it has to show up consistently across multiple Pade approximates at the very same order. This just makes sure it's a real signal, not some artifact of one specific calculation. The second rule is complex G2, or N stability. As we feed the engine more and more terms of the series, as we increase the truncation order N, a true physical singularity should converge to a stable location. If a root just jumps around all over the place, it's nothing more than numerical noise. So only the poles that pass both the G1 and the G2 filters are considered real evidence. Okay, let's head to the evidence room. For the big visual test bed, the paper zooms in on the Class C orbit ladder. You might remember this one,
It was the problem child from the conformal atlas back in paper 24. Definitely the most difficult case. So, what does our new complex probe reveal here?
And here it is. This is really the visual climax of the whole investigation. What you're looking at is a heat map of the inverse Pade denominator, where the bright spots, those are the poles. The red cross marks our target, S equals 1.0. And that dashed box? That's the Feigenbaum neighborhood. That's exactly where the singularity should be, if it were merely displaced. And, well, just look. It is structurally, profoundly empty. The few poles that do exist are nowhere near our region of interest. The suspect is not at the crime scene, period.
And that stunning visual from the heat map? It wasn't a fluke. The summary table from the paper confirms that the result was universal. Just look down that column. 0, 0, 0, all the way down, across all 6 ladders. Not a single G1/G2 stable pole was found inside the search radius for any observable in any regime. The evidence is just systematic and overwhelming.
So this all builds to the final verdict. With the synthetic tests passed, the rules of evidence established, and the huge 6-ladder search coming up completely empty, the conclusion becomes pretty much inescapable.
And the paper states it without any ambiguity. I'm quoting directly here. The Feigenbaum singularity is absent from the complex Borel neighborhood, not merely displaced off the real axis. The key point here is that the search didn't just find nothing on the real axis, it found nothing in the entire complex neighborhood. This isn't just a failure to locate a suspect, it's strong evidence that the suspect doesn't even exist anymore. It's destruction, not displacement.
This table just brilliantly sums up the state of the case after paper 25. The full Feigenbaum atlas is now complete, and every single cell is negative. The gamma family on the real axis, the conformal family on the real axis, and now the gamma family in the complex plane. Across every regime and every observable, the verdict is exactly the same. The singularity is gone.
So, the case of the missing singularity is closed. The what is settled. But, this answer just opens up an even deeper question. The next case file is already open for paper 26, and its mission is purely analytic. Why? Why does this specific non-holomorphic perturbation cause total destruction of the Feigenbaum singularity instead of just shifting it? That's the mystery we'll be tracking next.